Hey, Shalma. So today I would like to tell you about one of the most exciting series of events that have unfolded in my long career as a physicist. It goes back it started about 12 years ago for me, and it involves the discovery of this weird signal from the center of the Milky Way that we call the galactic center gamma ray excess. We still don't really know what this is all about. The dust has yet to settle on this problem, but it might be telling us something about what the nature of dark matter is. And watching this data kind of unfold and the story come together, well, it's been one of the biggest thrills of my career and life so far.
Okay, wow. So you're very, very close to the story that we're about to tell about this one particular blip in the data that people agree and then disagree about.
Painfully close to the story, yeah. This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses on subjects including history, philosophy, literature, math, and science. For me, it's like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee and all in the comfort of your own home or daily commute. One of my favorite courses offered by Wondrium is called Redefining Reality. Over 36 lectures, this course explores some of the biggest picture questions in all of human thought, spanning not only physics and other branches of science, but also the metaphysics and philosophy that underpins it. In this course, you'll explore questions like, are atoms real, or can even be said to be real? Or can the physics of quantum mechanics somehow help us to explain the phenomena we call consciousness? So if you want to learn about some of these deep questions at the heart of our understanding of reality, give this course a try. You can sign up for Wondrium now through our special URL to get a free month of unlimited access. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermi Lab and at the University of Chicago.
So let's go back to the beginning.
So back in 2009 or so, like usual, I was thinking about a lot of different things in physics. So in preparation for this podcast, I went back and looked at what papers I wrote around 2009, and they're on all sorts of different topics. I wrote some papers on cosmic rays. I wrote some papers on dark matter candidates that appear in these things called Kaluza-Klein theories that we've talked about in earlier episodes of this podcast. I wrote some papers on neutrino astronomy. I talked about the role that dark matter particles might have played in the fairly early universe, what we call the dark ages of the universe. I wrote some papers on pulsars. I wrote a bunch of different things.
Okay, now it just sounds like you're bragging.
It was a busy time, you know. I'm not saying these papers were all great. Some of them I'm proud of, but it was a lot of papers. I think I can objectively say that. But more than any other topic around that time, I was fixated on how we might detect the energetic particles that could be produced when pairs of dark matter particles come into contact and annihilate themselves.
In other words, you really wanted to be able to detect the dark matter, and
That's right.
You were studying, the ways that it could happen.
Yeah, and in my view, back then and even now, this is one of the really exciting ways to look for, signs of what the dark matter consists of. So, of course, we know dark matter exists. We see its gravitational influence in any number of different ways, but we don't know what the pieces, the particles that make up the dark matter are. This is one of the ways that you could hope to learn that.
You're not talking about seeing a dark matter particle itself. You're talking about, the ways that those dark matter particles could interact, like maybe two of them annihilate and form, some other particles that you can see, and then you can kind of deduce backwards that they came from dark matter. So it's this kind of like indirect way to see the dark matter.
Yeah, in fact, this is called indirect detection for that precise reason. Yeah. So as it turns out, not just in like one particular theory, but in lots of different theories of what dark matter might be, those dark matter particles can be stable in isolation. Like if you just sit a particle of dark matter on its own, you can wait, a trillion years and will still be there. But when you get pairs of dark matter particles together, they can basically destroy each other or annihilate, having their mass converted into other forms of energy. So you might make energetic electrons and positrons, or you might make energetic neutrinos, or you might make energetic photons, which we call gamma rays.
You can see those gamma rays and then deduce that they came from this dark matter annihilation.
Yeah, that's right. So we know approximately anyway where the dark matter is. So we know how the gamma rays from dark matter should be distributed across the sky. We also can calculate for a given theory what the spectrum should be of those gamma rays, namely like how many of them should have different amounts of energy and things. And, based on arguments about how the dark matter may have been produced in the early universe, we can estimate how bright this overall signal should be. So we have a pretty concrete, expectation for what this signal, if it exists, should look like. And lots of us were excited back in 2009 or so to start looking for it. So the main reason why this was such an exciting topic around 2009 was that all of these astrophysicists just got a brand new telescope to look for this sort of thing. So technology drives a lot of innovation in science, and this was no exception. So this particular telescope is called the Fermi Gamma Ray Space Telescope, and it was deployed on a rocket and then a satellite in June of 2008. So since then, it's been up in orbit, recording gamma rays that strike it from all directions of the sky. We've got 13 years of data now or something. So it's had quite a mission. So the idea that dark matter particles might produce gamma rays that we could detect goes back a long way. I think there were papers in the late 70s about this. And people have been writing papers at an increasing pitch ever since then. But back then, of course, there were none of the telescopes you would need to do this. When I was a grad student in the early 2000s, I wrote a paper about how the Egret telescope, kind of Fermi's predecessor, might be able to do this. But even back then, it was really clear that all of our favorite theories were out of the reach of something like Egret. We need something like Fermi to meaningfully test, what we considered to be the most well-motivated and attractive theories of dark matter.
Right, which is why it was so exciting to finally get that data, right? That was 40 years of, theory papers that were saying, maybe this will happen, maybe this will happen. And now you can finally look at the real world and see if it does.
Yeah, and it's one thing to write a paper saying, well, we've looked at the data from this telescope and we can put an upper limit that's, 10 or 100 times bigger than what we expected dark matter to produce. That's okay. You don't really learn that much. You learn a little bit. But with Fermi, you should really be able to get to the expectations of what dark matter was what we thought should produce. At least if we got a little bit lucky, that would happen. We were like building up to what we hoped to be a discovery mission. All right. So in the years that were leading up to Fermi's launch, I and other people were trying to figure out as precisely as we could what the signal from dark matter would look like and how we would separate that signal in the future data from other kinds of gamma rays that might come from other astrophysical processes or sources. We put a lot of work into ways that we could tell this hypothetical signal of dark matter annihilation apart from the other ways that gamma rays are made in our universe. All those calculations we did in those years leading up to Fermi taught us a number of things about what this signal from dark matter, if it exists, would look like. For one, it should be centered around the middle of our own galaxy. That's where the most dark matter is. So right around our own galaxy's supermassive black hole and kind of going out in uniformly in all directions. So it should be kind of a round blob centered at the middle of the galaxy, brightest in the center and becoming fainter as you go off in any given direction. And also there should be a peak in the spectrum, by which I mean the photons would kind of cluster around a common energy, and that energy would be related to the mass of the particles that were doing the annihilating. So these were two, features we would look for in the future data. And it was hoped anyway that if there were a signal bright enough with those features, we could tell it apart from all the gamma rays that might come from other astrophysical sources or mechanisms. So during the first year that Fermi was in orbit, it was collecting all this data, and that data was really only usable by people who were members of the Fermi collaboration. So these are the scientists who actively worked to build and develop Fermi. But after a year, that data went public to people like me who aren't inside of the collaboration. So at that time, with a lot of eagerness and enthusiasm, I downloaded the data with my collaborator, Lisa Goodenough, who was a grad student at NYU at the time. So Shalma, you're in good company.
Good enough company. Yeah.
Good enough, yes. I'm sure she's never heard that joke before. So we had written this code to try to analyze this data to look for a signal of dark matter, like a dark matter like signal of gamma rays in this data. And if I'm being honest, we didn't really expect to see a signal like that. With this first data and this first pass through it, we kind of expected just to be able to place an upper limit. Like there can't be more than so many dark matter annihilations going on. And we might write a nice little paper saying dark matter does annihilate more often than this. And here are some theories that are ruled out that didn't used to be ruled out.
Right. That's kind of like the reality for physicists like us, is that we don't really expect to discover things in most of our research.
That's right. Most physicists will, even really good physicists who have great careers and highly cited and all this stuff, will probably never make a legit discovery in their career. They'll make insights, they'll refine our understanding, that, whatever, but like discoveries are really rare. If they, that's why they're so treasured, that's why they're such a big deal. And there are a lot of physicists and not that many discoveries. So, the number of discoveries per scientist is really, really small.
Right. So you were not expecting to see any dark matter in this first, round of data analysis.
Not really. No. I was looking to make a nice paper ruling out somebody's favorite theory. And I still remember the morning where like we rendered the spectrum of the signal for the first time. I'm sitting there in my Fermilab office, my feet are on my desk, as they often were in those days. Like run code, fix bug, plot. And this spectrum comes up, which is this weird bump in it. It climbs really fast. It reaches a peak at an energy of a few giga-electron volts, and then it falls. And I'm like, oh, that's weird. And I wonder what I did wrong, because that's not what it should look like. That looks too much like dark matter. So, I check things. Lisa checks things. We go back and forth. We, troubleshoot. We whatever. And it's just not going away. I mean, we can change its characteristics a little bit here and there by making different choices. But there's this bump there. And it looks pretty spherical, and it looks pretty centered on the middle of the Milky Way, and its spectrum looks like that from dark matter. So, we didn't think we had a lot of choice but to write a paper saying this might very well be dark matter.
So when you saw this, I mean, did you feel like you just discovered dark matter? Like, what was the feeling? Or were you like still like doubting it and still not even sure yourself?
I felt similar then to how I felt a couple of earlier times in my career, when I'd written papers saying, here's a weird signal that's hard to explain. Maybe it's dark matter. And I kind of sketched how that might work. In none of those times did I think it was more than 50-50 likely that it was really dark matter. Probably a lot less than 50-50, in fact. But did I think it was worth thinking about as a possible signal of dark matter? Yes. And I thought similar things at this point. And you can kind of see this in the title we gave our paper. So we wrote this paper over a period of a couple months, and we titled it Possible Evidence for Dark Matter Annihilation in the Inner Milky Way from the Fermi Gamma Ray Space Telescope. Like possible evidence. Like, we're not even willing to call it evidence yet.
Right. You weren't coming in being like, we discovered dark matter detection. You were saying, here, what do you guys think?
Yeah, that's right. And that approximately reflects our real thinking at the time. Sometimes people write provocative titles or really conservative titles that don't reflect their true opinion. This approximately reflected at least my opinion at the time. So the paper received a bit of attention, but it didn't convince very many of my colleagues that we've really detected dark matter. People in general were very skeptical, maybe didn't believe we had done things at the level of precision that were required to really, convince you of something this important. And they had some good points. Some of the criticisms were fair. We had treated the instrument's response in a pretty simple way. As it turns out, it doesn't really matter if you get those details right. You get the same basic features out. But that being said, we could have done it better.
Wait, by that you mean how the detector deals with the data it's receiving? How it could have an impact on what it looks like?
So when the telescope measures one gamma ray, it measures how much energy that gamma ray has, and it measures what direction it came from. But they measure these things imperfectly. So to go from the thing you measure to the thing that's you're measuring, the thing that produces the signal, you need to take this imperfection of the instrument into account. We call this stuff like the point spread function and things like this. So, I had a pretty simplistic model for Fermi's point spread function. We could have done better. And in subsequent papers, we did. The other thing that people, I think, fairly criticized us for is that we had a pretty simple model for the astrophysical emission. We didn't get a lot of, it wasn't a detailed model, it wasn't a complex model. And people weren't at all sure that astrophysical sources or mechanisms couldn't make the signal that we were talking about. And I think that was fair at that point.
Mm-hmm. Right. So in other words, people were like, how could you be sure that this is dark matter and not just like some certain kind of pulsar or some certain kind of star or something like that?
And my answer was we weren't sure. So, I think we were being pretty honest. But then we went back, and over the next couple of years, I wrote a couple of other papers on this data set. So by this time, there was even more data, and our techniques were getting refined. We were more careful and more precise. The first of these papers was, again, co-authored with Lisa Goodenough, and the second one was with Tim Linden, who at the time was a grad student at the UC Santa Cruz. Basically we did everything we could to improve these analyses and respond to all the criticisms that had been leveled at the earlier papers. And we kept seeing this big, bright, dark matter-like signal. In every way we could measure this signal, it looked like what we'd expect dark matter particles to produce.
So at this point, were you, how are you feeling now? Were you getting more and more excited?
Yeah, I was.
Did you have any thought that was like, I'm going to win the Nobel Prize for discovering?
We don't talk about that, Shalma. There's certain things. I mean, I'm not a superstitious person, and also, no one should ever talk about that in that context. So we're just going to leave that one, unspoken. All right. So by the end of 2012, I was pretty convinced the signal was there and it was real. That doesn't mean I was sure it was from dark matter. I wasn't, but I was sure the signal was there and it at least looked like the sort of thing dark matter would make. And in that same year, there were a couple other groups independent of our own that saw the same signal in the data. One was from some people at UC Irvine and one was from some people in New Zealand. So there started to be a consensus forming that the signal was real.
In other words, it wasn't a statistical fluke or something. Like the bump
or just
was really
us screwing up.
Yeah.
Yeah. I mean, this gave people confidence that we hadn't just done it wrong, which, I was pretty sure we hadn't. I knew how careful we had been. But, to convince other people, it's good to have other people, take their own approach of the problem and get the same answer. So to advance the story, though, we needed kind of more heavy firepower. So in 2013, I started to assemble a collaboration of scientists that I thought would bring a lot of weight and expertise and skill to the problem. And we all worked together. This included Doug Finkbeiner at Harvard, Tracy Slatcher at MIT, Tim Linden again, who was at the University of Chicago at that time, and a couple of their grad students, Nick Rod and Tanzu Dalen. So we worked for over a year on this, and it was a pleasure working with these scientists. This is like the dream team of people for me to do this kind of problem. And after about a year, we had thrown every trick and tool we could think of at the problem. We had, done every test. We had plotted every relevant thing, and everything we had done made it look like the signal was there and it had all the features that dark matter particles would be expected to produce. So in particular, it looked spherically symmetric. It didn't seem like it was stretched along the plane of the Milky Way or anything. It looked like a big round blob like you'd expect. It got brighter as you moved in towards the center at about the rate that, people had expected from dark matter. The spectral shape, or how many photons there were of different energies, looked just like right out of the box dark matter models predicted. And the overall brightness looked like what you'd expect of a particle that would have been produced in the early universe with the quantities that would account for the dark matter. So in all of these ways, like check, 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 it looked like dark matter. And we couldn't think of any like astrophysical mechanisms that would do quite as well to explain this.
Okay, so now at this point, I feel like people listening will be like, did you not discover dark matter? Like, why are you not more excited about this? This sounds incredibly promising. So,
well, first of all, I am really excited about this. I'm an enthusiast about the galactic center excess and the possibility that it's dark matter, but we're not sure that it's dark matter. I will make that perfectly clear.
And also, not everyone thought the signal was as promising as you did, or you wanted it to be, right?
Yeah, I think with this Dale et al. Paper, the 2014 paper, there was an explosion of interest. So we convinced a lot of people that this was very, very promising. I don't know how many hundreds of papers got written on this topic in the months after that, but it was hundreds. Lots and lots of papers on the subject. People were very, very excited. But there were other ideas out there for what could make this sort of signal. So obviously it could have been dark matter. But people started also talking about maybe there had been events in the past where the center of the Milky Way, either through something to do with the black hole or maybe something to do with the stars, stars in that cluster in the very center, maybe produce these like bright bursts of cosmic rays. And then those cosmic rays would fly outwards, interacting with things like gas or radiation to make gamma rays that might look a lot like a dark matter signal. I think at the time that was promising. At least some of the theories could kind of look like the signal we had seen. But as time went on, that looked harder and harder to do. I wouldn't say it's impossible now, but it requires a really special model that is has some very carefully chosen properties to make sure that it looks like a dark matter signal. So it would be a bit of a conspiracy if that's what the answer is. So I don't know. The cosmic ray outbursts to me don't look that promising anymore.
Are there people who still believe that it could be cosmic ray outbursts?
Yeah, so cosmic ray outbursts have definitely become less popular as time has gone on. I don't know anybody who thinks that's the most likely explanation, at least that has told me that.
People are careful what they say to you about the galactic center.
Oh, not that careful. People are happy to argue with me, and they should be. But I think the idea, other than dark matter, that has gained in popularity in that window of time is that it could be a large collection of objects we call pulsars. Like this is, I would say, probably the most popular idea out there, and more than probably, it is the most popular idea, and for some pretty good reasons. So, if you just look at pulsars that we can clearly see with gamma ray telescopes, they have a spectral shape that's pretty similar to the galactic center excess. So that could be a coincidence. And if it's dark matter, then it is a coincidence. But it definitely gives you reason to pause and think, well, maybe there's just a bunch of pulsars in the galactic center distributed in a spherically symmetric way, kind of like dark matter is, with a lot of pulsars in the middle and then kind of falling off in all directions. And maybe that's what's responsible for the signal. I think that's at least a logical possibility that we should contend with. Regardless of how likely you think that is, that's definitely the sort of thing you would have to work to rule out before you'd be convinced that you're looking at dark matter annihilation with the Fermi data. So
you're saying that this is currently the more popular opinion over it being dark matter. So I guess I'm curious, dark matter, we've made episodes about how well motivated dark matter is. How well motivated is this, conveniently distributed set of pulsars? Why do people believe that more than they believe that this is dark matter?
So, I think the main reason why people tend to gravitate towards pulsars as an explanation is because we know pulsars exist.
I thought you were going to say because of theory of gravity.
No, so the gravitate. Yeah.
They are pretty heavy usually.
They are. But really though, we know pulsars exist. We know they make gamma rays. So it's a pretty conservative opinion to say, well, maybe they're just a few tens of thousands of these things clustered around the galactic center, and they coincidentally make a signal that looks what people are looking for from a sign of dark matter. I don't fault anyone for that opinion. That sounds pretty reasonable to me. That being said, there are a lot of challenges that go with that interpretation. In particular, we haven't seen any pulsars in the inner galaxy, at least not of the kind that would make gamma rays like this. And you would expect that if there were that many pulsars in the inner galaxy, that we should have resolved the few of the brightest ones by now, maybe 10 or 20 of them or something. We haven't. So maybe these are slightly fainter pulsars than we see elsewhere. Maybe there are more of them and they're fainter, and that explains why we haven't resolved individual ones. And then there are other things. Generally speaking, where you find these kinds of pulsars, you also find objects called low mass X-ray binaries, which are kind of the evolutionary precursor to this kind of pulsar. But we don't see nearly enough of those in the galactic center either. So arguments like this make me downweigh the probability that the signal comes from pulsars, not rule it out, but downweigh it a bit in my own estimation.
So what do you think the breakdown is? What percentage of people believe this is dark matter versus pulsars or some other, just random astrophysical thing?
So when you go around asking physicists what they believe, the most common answer you get is, we don't like that word, believe, right? And if you ask me that question, I can give you probabilities, but I won't, it's not something that I think is black and white. I personally think it's pretty likely or reasonably likely that it's the signals from dark matter, but I wouldn't say I'm 90% convinced. Maybe I'm, 50, 60, 70% or something is kind of where I kind of come down. And by the way, that's a huge number for a discovery hypothesis, right? I've not felt that way about any other exotic physics claims I've been part of in my career. But I think my number is probably much higher than the average in the community. I'm sure it is. I think a lot of people out there who are kind of know a lot about this will give you numbers like 5, 10, 15%, things like this, but with a huge variation from person to person. And I think a lot of that is just, we see a lot of anomalies come and go. Most of them turn out to be explained by something pretty mundane. So if you're just a betting person, you'll be well served by betting on the mundane resolution to whatever problem you're facing.
Right. And I guess you're right. Believe is maybe the wrong word, because at the end of the day, we're going to find out. It's hard to tell.
This won't remain an open question forever.
But it won't. It's very much, something that we can test.
So let's talk about how we move forward. How do we answer this question? Because, I'm confident that the day will come where, the people who think it's pulsars and the people who think it's dark matter will agree one way or the other.
Right. And that's how science works, I guess. Yeah.
Maybe even a none of the above answer. Who knows? But there are at least 3 good avenues, I think, to resolving this question. First of all, there's dark matter in pretty large quantities in these things called dwarf galaxies, but there aren't thought to be very many pulsars or other sorts of astrophysical gamma ray emitters there. So as our gamma ray telescopes get a little bit better, and as our surveys looking for these kind of dwarf galaxies get better, in particular the Rubin Observatory, which is going to happen pretty soon, we're going to have a bunch of dwarfs to look at, and we're going to see if the gamma rays from those dwarfs look like the gamma rays from the galactic center. If they do, that's a big plus for dark matter, maybe even a definitive one. And if the signal's just not there, we'll be forced to say, well, I guess it can't be, simple annihilating dark matter that's producing that signal. So that should be pretty straightforward, although, we need a lot of data first. So the second way that I think we can like discriminate between these hypotheses is using these kind of future radio telescopes, these big, deep radio surveys that should be able to detect the kinds of pulsars that it would take to explain the signal in the galactic center. So in particular, like the square kilometer array called SKA, which is kind of a futuristic but awesome radio telescope. In its kind of full glory, it should be able to detect hundreds of these things, these pulsars, if they're there and if they explain the signal. So either they're going to see those pulsars or they're not. And if they see them, well, people like me will concede that it must be pulsars that make the signal. And if they don't, it would make it very hard for people to argue pulsars are responsible, thereby bolstering the dark matter interpretation. And then the third thing is just we keep doing the stuff we've been doing, like with Fermi, but with new telescopes and more data, refining all this stuff. And there's there are a variety of future gamma ray telescopes that will have information to bear on this. There's a shrink-off telescope array, which will observe this part of the sky with much greater precision than is currently measured, but at higher energy. So you won't see this excess itself, but you'll learn about the environment, and that will help us kind of unravel this mystery. And then at lower energies, there's plans for a satellite mission. It goes by the name of Amigo or Astrogam. Those are some of the names of this proposed mission. And it's another gamma ray telescope, kind of like Fermi, but it's best at lower energy. So again, it will kind of help complete the picture, teach us things we don't currently know. I would say that once you have that data in hand, the picture will become much clearer one way or the other.
Right. So, eventually we'll know whether this is dark matter or not, but it's exciting to think about it being dark matter, right? So what would we really get out of this being dark matter? Like, what would happen next besides you winning lots of fame and fortune?
So my eyes are rolling, by the way. I just want that to go on the record. Okay, if you just surveyed physicists and said, like, what question do you want an answer to? Like, what do you really want to know? I have to think that the nature of dark matter has to come pretty high on that list. That is one of the big mysteries, and to know like the quantum particle nature of dark matter and what it is and how it fits into our universe's laws of physics, that's got to be a pretty big goal. And this is, kind of the first step. If it's true, this will be the first step towards really figuring that out. We'll be able to measure things like how heavy these particles are, what kind of particles they produce when they annihilate, what rate they annihilate at, which all we can then filter into what kind of particle this must be.
Right, which is all stuff we have no idea about right now.
Yeah, that's right. We have various lines of speculation, but no real measurements to inform us, right? If you're asking me, though, what's important about this, I mean, it's of course important to know what the dark matter is. It's part of our universe, and that's important. But the thing I'm maybe even more excited about is that this gives us a lever to learn about the very early universe. So at present, we can measure the cosmic microwave background, which tells us a lot about what the universe was like a few 100,000 years after the Big Bang. We can measure the various abundances of different nuclei that were formed in the Big Bang. And this tells us what our universe was like, seconds and minutes after the Big Bang. But the kinds of dark matter particles we're talking about here would have been formed like a millionth of a second or so after the Big Bang. So if you can measure the properties of this particle and deduce how much should have been produced in the Big Bang, and that in turn matches how much dark matter there is in our universe, you've just learned things about how our universe was expanding and evolving a million times earlier than we currently have any kind of empirical evidence for. So moving that yardstick backwards and closer to the Big Bang, to me, is maybe even more exciting than learning what dark matter itself is.
So how upset would you be if it isn't dark matter? Would it be like a heartbreak, or is it like, because you've been very measured the whole time you were never like, I know for a fact that this is dark matter, I'm sure of it in my gut. So, have you kind of accepted the possibility that it's not?
I mean, I would be disappointed. I'll have to make myself a stiff drink or two when they discover those 100 pulsars with the square kilometer array or whatever. But no, I mean, I'm not convinced it's dark matter. I'm not certain it's dark matter, and therefore I'm open-minded to it being something else. I feel lucky to have been part of this story, even if it turns out not to be my preferred outcome. That being said, I mean, when that data is about to become available, am I going to cross my fingers and, really hope for a dark matter like outcome? Yeah, of course I am. That would be incredibly exciting. I could live many careers as a physicist and never have anything quite that cool happen again, So, I know what I'm hoping for, but, I'll try to be measured and accept it if it turns out to play the other way.
Mm-hmm. And I'm sure all those people who wrote the papers being like, this could be pulsars, I'm sure like deep down they hope that it's not too. I'm sure they hope that it's the dark matter.
Yeah. I mean, it's not hard to make, if you're choosing, like I get to decide if it's going to be dark matter or pulsars, it'd be hard to imagine many people going at pulsars. Like we all, we're scientists. We want the big, awesome thing to happen. And the discovery of dark matter would certainly be a big, awesome thing.
Thank you so much for listening to Why This Universe. If you want to support us more and get access to some exclusive content like exclusive interview clips, Ask Me Anything episodes, the opportunity to ask us questions, and a free sticker, you should definitely join us on Patreon. You can find us at patreon.com/whythisuniverse, and we really appreciate all the support that we get through there. Today's episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermi Lab. He's also the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. And Why This Universe is brought to you by the University of Chicago Podcast Network.